Welcome to this rigorous lecture on how to validate AI-based research gap discovery. Today we'll learn to treat gap discovery not as a magic black box, but as a scientific experiment requiring systematic validation. Let me start with a fundamental question. Can we trust a machine to tell us what's missing in science? The answer is, not without rigorous experimental validation. I can suggest gaps, but only humans can verify them through systematic empirical testing. Think of AI as a hypothesis generator, not an oracle. Every gap it suggests is a hypothesis that must survive skeptical scrutiny. We will walk through an 8-step validation workflow. Each step is designed to reduce false positives while maintaining scientific rigor. Here's our workflow. We start by defining a narrow domain, build a corpus, extract claims and relations, generate candidate gaps, then validate through human verification, persistence testing, and hypothesis generation. Step 1. Define a narrow domain. This is absolutely critical. You cannot discover meaningful gaps in all of machine learning or all of biology. A bad domain definition would be machine learning. That's far too broad. You'll drown in irrelevant papers and spurious gaps. A good domain definition is graph neural networks for protein folding. This is specific enough that you can actually read the key papers and verify claims. Here's a rule of thumb. Can one expert reasonably know 80% of the key papers in this domain? If not, it's too broad. A good target size is between 50 and 500 papers. Below 50, you don't have enough material. Above 500, you're likely too broad. Let me give you a concrete example of domain scoping. Deep learning as a domain has over 50,000 papers. This is unmanageable. But attention mechanisms for time series forecasting has about 200 papers, and one expert can reasonably verify the key claims. Step 2. Build your corpus. This is the foundation of everything that follows. Use multiple sources. RS4 for preprints, PubMed for biomedical papers, Semantic Scholar for cross-disciplinary coverage. Apply a quality filter. Set a minimum citation threshold, or only include papers from top-tier venues. This reduces noise substantially. Choose a time window. For fast-moving fields like deep learning, 3 to 5 years is appropriate. For slower fields, go back further. Let's do a back-of-the-envelope calculation for corpus quality. Assume your narrow domain produces 100 papers per year. You set a citation threshold of 5 or more citations. Empirically, about 30% of papers exceed 5 citations after 2 years. Over 5 years, that gives you 100 times 5 times 0.3, which equals 150 high-quality papers. This is an excellent corpus size. Step 3. Extract claims and relations. This is where natural language processing and large language models come in. What is a claim? A claim is a falsifiable statement extracted from a paper. For example, Model X achieves 92% accuracy on dataset Y. What is a relation? A relation connects two concepts. For example, batch normalization improves training stability. This connects batch normalization to the concept of stability. From raw paper text, we extract structured claims and relations. The claim is that dropout reduces overfitting. The relation is dropout mitigates overfitting. Use large language models with carefully structured prompts for this extraction. GPT-4 or Claude can do this reasonably well. But you must verify extraction quality. Take 20 to 50 random samples and manually check that the extracted claims match the paper content. Step 4. Generate candidate research gaps. This is where the AI really shines. Let me define what we mean by a research gap. A gap is a combination of concepts, methods, or datasets that appears feasible but has not been explored. Type 1. Method dataset gap. Algorithm A has been tested on datasets X and Y, but not on dataset Z, even though Z is relevant. Type 2. Combination gap. Techniques A and B have been used separately, but their combination has not been tried. Type 3. Extension gap. Method A works for problem class 10, but could plausibly be extended to problem class Y. For example, we know transformers work well on text and images. The A, I might suggest, What about multivariate time series? This is a plausible extension gap. How does the AI generate these gaps? Strategy A. Enumerate all methods and all datasets. Find combinations that are plausible but missing from the corpus. Strategy B. Look for technique pairs that appear separately but never together. This suggests a combination gap. Strategy C. Look for asymmetries. If subfield A uses method X heavily, but related subfield B never does, that's suspicious and worth investigating. Here's a key question. How many candidate gaps should you generate? Too few, and you might miss the best opportunities. Too many, and validation becomes impossible. You can't manually check 1,000 gaps. The sweet spot is 50 to 200 candidate gaps. This is large enough to capture diversity, but small enough to validate. Step 5. Select a sample for human verification. You cannot verify all gaps. You need a sampling strategy. Random sampling is unbiased, but may miss the most interesting gaps. Stratified sampling ensures you get examples from different gap types. Method dataset gaps, combination gaps, extension gaps. Confidence-weighted sampling focuses on gaps where the AI is most confident. This is efficient, but introduces bias. A practical formula: sample size equals the maximum of 30 or 15% of total gaps. This ensures statistical validity. From 150 candidate gaps, we sample 30 using stratified sampling. Human reviewers then evaluate each gap for validity, interest, and feasibility. Step 6. Test whether gaps persist after reading the key papers. This is the most critical validation step. Why is this necessary? Because A, I might miss papers, misinterpret claims, or fail to recognize that a gap has actually been filled. Here's the protocol. 1. The AI suggests a gap. For example, method X has not been tested on dataset Y. 2. A human expert identifies the 5 to 10 most relevant papers in that area. 3. The human reads these papers carefully, looking for any mention of method X applied to dataset Y, even in passing. 4. The gap is considered valid only if it's still absent after this careful reading. Let me give you a real example from natural language processing. The AI suggested this gap. BERT has not been fine-tuned on legal text for case outcome prediction. A human expert reads 8 key papers on legal natural language processing. The human finds that one paper from 2020 did exactly this. The gap is false. Why did the AI miss it? The paper was published in a law journal, not a computer science venue, so it wasn't in the corpus. This is why human verification is absolutely essential. No corpus is complete, and no AI is perfect. What persistence rate should you expect? Typically, 40 to 70% of AI-suggested gaps will survive human verification. If your persistence rate is below 30%, your AI gap detection is too noisy. You need to improve your extraction or gap generation. If your persistence rate is above 80%, your AI is too conservative. You're only finding obvious gaps that any expert would spot. Step 7. Generate one testable hypothesis for each validated gap. This is where science happens. Remember, a gap is not research. A gap is just an observation. You need to convert it into a testable hypothesis. Bad hypothesis. Method X has not been tested on dataset Y. This is just a gap statement. Good hypothesis. Method X will outperform the current baseline by at least 5% on dataset Y, because X has property P, which is advantageous for Y's characteristics. A good hypothesis has 4 components: a specific measurable prediction, a clear baseline, mechanistic reasoning, and falsifiability. Let me walk through hypothesis generation for a concrete gap. Validated gap. Transformers have not been applied to electroencephalography signal classification. First, ask, why might this work? Reasoning. Self-attention mechanisms can capture long-range temporal dependencies, which are known to be important in EEG signal analysis. Hypothesis. A transformer-based model will outperform convolutional neural networks by at least 8 percentage points on sleep stage classification, as measured by macro F1 score. Baseline. The current best convolutional neural network achieves 0.78 F1 score. Target. our transformer should achieve 0.84 or higher F1 score. This is now a testable scientific hypothesis that can be empirically evaluated. Step 8. Submit your hypothesis to expert critique. This is the final validation gate. Find 2 to 3 domain experts who are not collaborators. They should be skeptical and knowledgeable. Ask them 3 critical questions. Question 1. Is this hypothesis actually novel, or does it exist in the literature? Question 2. Is the mechanistic reasoning sound, or are there obvious flaws? Question 3. Is this hypothesis worth the effort of testing? Will a positive result be meaningful? Survival criterion. At least 2 out of 3 experts must say yes to all 3 questions. If not, go back and revise. Here's a scorecard example. Expert A approves all 3, Expert B rejects the reasoning, Expert C approves all 3. Result: the hypothesis passes with 2 out of 3 full approvals. Why does this 8-step protocol matter? Without systematic validation, AI-based gap discovery is just hype. It's pattern matching without understanding. With rigorous validation, it becomes a scientific instrument that can genuinely accelerate discovery. Think of it like calibrating a telescope. The telescope can see far, but you need to verify that what you're seeing is real and not an artifact. Let's estimate the time investment for this workflow. Steps 1 and 2, domain definition and corpus building, take about 2 weeks of focused work. Steps 3 and 4, extraction and gap generation, take about 1 week if you're using good tools. Steps 5 and 6, sampling and human verification, take 3 weeks. This is the most time-consuming part. Steps 7 and 8, hypothesis generation and expert critique, take 1 week. Total time is approximately 7 weeks for a rigorous validation pipeline. This is substantial but worth it. How do you measure success of this workflow? Metric 1. What fraction of AI suggested gaps persist after human reading? Target: 50 to 70%. Metric 2. What fraction of generated hypotheses survive expert critique? Target: at least 40%. Metric 3. What fraction of tested hypotheses lead to publications? Target: at least 30%. This is the ultimate validation. Let me highlight common pitfalls that students encounter. Pitfall 1. Skipping the narrow domain definition. Students try to find gaps in all of deep learning. This never works. Pitfall 2. Trusting AI output without verification. 30 to 60% of AI suggested gaps are false positives. You must check. Pitfall 3. Stopping at gap identification. A gap is not a contribution. You need a testable hypothesis. Pitfall 4. Not seeking expert validation. Your hypothesis might be obviously flawed to someone with deep domain knowledge. Let me discuss an advanced topic. How do you score gap quality? Dimension 1. Feasibility. Can this gap be tested with currently available tools and datasets? Dimension 2. Impact. If the hypothesis is confirmed, how significant would the result be? Dimension 3. Novelty. How surprising is this gap to domain experts? You can create a weighted score. Gap score equals weight 1 times feasibility, plus weight 2 times impact, plus weight 3 times novelty. A reasonable weighting is 0.4 for feasibility, 0.4 for impact, and 0.2 for novelty. Let me compare 2 candidate gaps using this scoring system. Gap A, transformers for EEG, scores 0.76. High feasibility, moderate impact. Gap B, quantum machine learning for drug discovery, scores 0.6. High impact but low feasibility. Gap A is better for a student project. Let's discuss statistical rigor for sample size in human verification. Why do we need at least 30 gaps for validation? The central limit theorem starts to apply at sample size 30. This allows us to make statistical inferences about the full population of gaps. The margin of error is approximately 1.96, divided by the square root of n. For n equals 30, that's about 0.36 or 36%. At 30 samples, your margin of error is 36%. This is acceptable for exploratory research. At 100 samples, margin of error drops to 20%. This is better, but requires more effort. Let me share a real case study from a student who used this workflow. Domain: few-shot learning for medical image classification. Corpus: 180 papers from 2018 to 2023, filtered by citation count greater than 10. Extracted: 420 claims and 280 relations using GPT-4. Generated: 95 candidate gaps using combination and extension strategies. Sampled: 35 gaps for human verification using stratified sampling. Persistence: 21 gaps survived human verification. That's 60%, which is good. Hypotheses: generated 5 testable hypotheses. Experts approved 3 of them. Outcome: 2 hypotheses were tested experimentally. 1 led to a publication in a top-tier venue. This is a success. Let me offer a philosophical perspective on this workflow. AI does not replace scientific thinking, it augments it. The human scientist provides skepticism, verification, and mechanistic reasoning. The AI provides systematic enumeration and pattern detection at scale. Together, they form a powerful discovery engine that is more effective than either alone. Think of AI as a tireless research assistant who reads everything and suggests connections, but still needs your judgment to separate signal from noise. What are the future directions for this methodology? Direction 1: automated hypothesis testing. Can we close the loop and have AI design and run initial experiments? Direction 2: multi-domain gap discovery. Can we find gaps that span multiple fields, enabling interdisciplinary research? Direction 3: real-time gap tracking. As new papers appear, can we dynamically update our gap database? Direction 4: collaborative platforms where multiple researchers validate gaps, creating a shared knowledge base. Let me summarize the complete workflow in one integrated view. This is the complete workflow. 8 steps from domain definition to expert-validated hypotheses. Each step builds on the previous one with increasing rigor. Let me leave you with 3 key takeaway messages. Takeaway 1. Treat gap discovery as an experiment, not a magic trick. Every claim must be validated. Takeaway 2. Human verification is non-negotiable. AI makes mistakes, misses context, and hallucinates. You must check. Takeaway 3. Aim for testable hypotheses, not just gap lists. Science advances through hypothesis testing, not through enumeration. In closing, let me offer a final reflection. This workflow is hard. It takes 7 weeks of focused effort. But it's worth it. The payoff is validated, novel, testable research directions that can advance your field. You're not just using AI as a tool. You're doing science with AI as a collaborator. And that requires rigor and skepticism. Good luck with your research gap discovery. Remember, validate everything, stay skeptical, and always ask whether the gap is real and worth pursuing.